Hey everyone, my name is Adonai. Today I want to take a look at this hierarchical enterprise network. So we have a access layer, distribution layer, and a core layer. We also have VLAN 10 for the staff end devices, VLAN 20 for the IT end devices, and VLAN 30 for the admin end devices. We also have VLAN 90 for the servers and VLAN 99 for the management VLAN. So we have 5 VLANs in total. We could use the management VLAN to assign management IPs to any of these access layer switches, and then we'd be able to ping to them for troubleshooting after we configure a default gateway on each of them. First one I want to take a look at is the SVIs on both of these core switches here. Okay, so as you can see, we have SVIs configured on each of these core switches. We have SVIs for VLAN 10, VLAN 20, VLAN 30, VLAN 90, and VLAN 99. Also have the same setup over here. So we'll be able to perform inter-VLAN routing via that method. The biggest problem I would say there is with this network is that we don't have hot standby routing protocol configured on all of the SVIs. So the only one that has hot standby routing protocol configured is VLAN 10. As you can see, we have the standby IP configured on core switch 1 and core switch 2. So if either of these go down, any of the devices in VLAN 10 will still be able to perform routing to the internet. We just won't be capable of inter-VLAN routing because we don't have hot standby routing protocol configured on VLAN 20, VLAN 30, or VLAN 90 and VLAN 99. So if core switch 1 goes down, because these PCs are using the IP address configured on the SVIs for core switch 1, they won't be capable of inter-VLAN routing or routing to the internet because the default gateway isn't using the HSRP IP, which has not yet been configured. So I just introduced that flaw so that we can be able to see what happens when that's incorrectly set up here. So we're going to get rid of core switch 1. Let's see what happens when we try to ping to the internet from PC 1. As you can see, we're still getting replies because of the standby IP configured over here. If you take a look at the IP address configuration on PC1, you see that the standby IP is configured here because we use that as the default gateway in the DHCP pool for VLAN 10. For VLANs 20 and 30, they're using the IP address configured on the D8 or on the SVIs for core switch 1. So if core switch 1 is down, we won't be able to route to other VLANs or the internet from VLAN 20, VLAN 30, VLAN 90, or VLAN 99. So let's try doing just that from PC1. If we try to ping to PC13, we fast forward a bit. As you can see, the requests are timing out. Just fast forward some more so that some more come in. It's not going through because we don't have any routing. So if we bring back core switch 1, let's see what happens when we test inter-VLAN routing from PC13 to VLAN 10. So let's do a ping to 10.10. Let's see, 0.14. That would be PC1. As you can see, now we're getting replies because its default gateway is back on the network. That problem wouldn't be happening if we configured hot standby routing protocol correctly on both core switches, but because we didn't, it only has one default gateway to work with, so if one goes down, there's no redundancy. The other biggest flaw I would say there is with this network is that we're not using a Ether channel protocol like LACP or PAGP, so there's not as much bandwidth available and there's not as much redundancy on the distribution and access layers. So if one of these links between the access switch and the distribution switches goes down, it can only reach one of the distribution switches. So let's say that this link right now that's up is removed. We can only reach the distribution switch 1. If we had LACP configured and we had LACP groups from access switch 1 to distribution switch 1 and access switch 1 and distribution switch 2, we would have 2 or more links between each of those distribution switches. So if one of those links went down, we'd still have the other one. And then we'd also have the combined bandwidth to work with. But because we're only using one link to each distribution switch, there's not as much available. Okay, so the last thing I want to talk about in this network is our NAT configuration. So let's pull up router 1. So on router 1, we have port address translation configured. The first thing you want to do, you want to look at your interfaces that are facing the inside network. So here it's gigabit Ethernet 8/0 and gigabit Ethernet 9/0. You want to go into interface config mode on gigabit Ethernet 8 and gigabit Ethernet 9. You want to run IPNAT inside. That's going to basically tell it that any incoming traffic on those interfaces needs to be translated to a public IP address, which would be this one. The next step is if you're using access control list as the source for IPs that should be translated, you need to create that access control list. So here we have IP access list standard pat list, and that's the name of the access control list. So here we're permitting 10.0.0.0, and then the subnet mask is going to be a /8 subnet mask. So we're allowing all of these VLANs and all the hosts on the VLANs, including the server. We're allowing all of those IPs to be translated whenever there's traffic going to the internet. And then next you would run this command. You'd run IPNAT inside source list, and then you put the name of your access control list for which command or which IPs you want to translate. And then you do interface fast Ethernet 0. So that's basically just telling it that this is your outside interface and to translate anything outgoing from this interface. And then this is very important. You want to put overload. If you don't put overload, it's just going to be a one-to-one translation. So only one device will be able to be translated at a time, and you'll have to wait between transmissions. If you do overload here, that allows it to use dynamic ports and create a socket pairing so that you can have multiple traffic flows outgoing to the internet at the same time, and all of the routers that will be en route to your destination and coming back will be able to track which device is actually sending and should be receiving that information. So that's all I have to talk about with this lab. I hope you enjoyed the video. Thanks for watching.